All right, CNT120, Chapter 4, we are looking at the section on Ethernet. So Ethernet now is your network access layer. Think about putting an Ethernet NIC in a computer. That NIC is essentially layer 2 and is connecting to the network either cable or wirelessly, and that is your layer 1. So installing an Ethernet NIC is basically my network access layer of TCP/IP. Makes a lot of sense to me. Ethernet is a layer 2 standard. Remember, once upon a time, computers were proprietary, so the networks that companies built were proprietary. Eventually, Ethernet kind of came to the top as the, hey, it works pretty good, hey, it's pretty inexpensive, and it became kind of the standard, the norm that pretty much everybody uses Ethernet now. But Ethernet 2 is the current Ethernet standard. This was actually developed by DEC, Intel, and Xerox, originally abbreviated DIX, before IEEE began to standardize Ethernet. It is actually composed of two sublayers. The data link layer of the OSI can be divided into two sublayers, the logical link control and the media access control. So if I take a look, here's my data link layer. I can actually break those two into the logical link control sublayer and the MAC sublayer. Well, the MAC sublayer is the one that's getting us access to the network. That's the one that's giving us the MAC address, media access control address. The logical link control sublayer is the IEEE 802.2 standard. This is the one that's interfacing with the protocols and things above, and handling things like multiplexing, flow and error control, reliability, that kind of thing. And that's standardized by IEEE 802.2. So an Ethernet frame, remember we have upper layer data like an IP packet or ICMP or ARP or things like that. And now we have the Ethernet header on the front. So the upper layer data is actually the payload part of my Ethernet frame, and there actually is a trailer on this guy now. There actually is an Ethernet trailer that is basically your checksum. So keep remembering the whole coming down through the layers, the data encapsulation process coming down through the layers, and each major layer is adding its own header. Well, Ethernet is now adding a header to, the IP packet, if you will. Now, the Ethernet header fields, we have these main fields right here, the preamble starter frame delimiter, destination source, and type, if you will. So if I take a look at these, the preamble starter frame delimiter, these are things we're not typically going to be able to capture off the network because they're serving a function. The preamble is a sequence of basically 1010101010 that is sent, and that is really to get the timing ready on the receiving end for, hey, you got a data frame coming, get awake, get paying attention, because we're soon going to be done with this synchronizing and actually to the real data. The starter frame delimiter is basically a 1-1. So it's kind of like 10101010. Okay, get ready, 1-1. Now all of that is done, and anything after this is now real data. So now we have the destination MAC address, followed by the source MAC address, and followed by the type field. Okay, the type field letting us know the upper layer protocol that would be inside. IP, ICMP, ARP, whatever it happens to be. And then we actually have the data from the upper layers, and then our checksum is in the trailer. Just like towing a camper, it's in the trailer. Here would be an Ethernet header. Just a couple fields, not many, but that is for our Ethernet network. Now the frame itself, if I take a peek, this is where they give you some numbers to give you the size of these things. The header and frame check sequence trailer make up the 18-byte frame. Header 14 bytes, trailer 4 bytes. The data may contain anywhere from 46 to 1500 bytes of info. So the minimum frame size, they're adding these up, would be 64 bytes, 18-byte frame plus a 46 byte of data, and the max frame would be 1518. Your 18-byte frame plus a 15-byte data. That's your typical frame size, Ethernet frame size. The maximum transmission unit, this is basically a value that says, hey, anything larger in here might need to be fragmented. And that can happen on low bandwidth links and that sort of thing. But using larger frames, you can, on some networks, you can use a larger frame and kind of get around this. Exceptions to this frame limit size are two things, VLANs and then jumbo frames. Well, VLANs, virtual LANs, Virtual LAN was a way to take a switch and break it into a couple logical networks, and then have nodes on different nodes on the switch on different logical networks, even though they're on one physical network. VLANs, to do VLANs, you have a VLAN tag that gets added in, so you have a couple more bytes that need to get used to identify what VLAN this frame traffic belongs to. So my maximum size can be a little bit larger. Jumbo frames, some networks use a proprietary version of Ethernet, allows for a jumbo frame, can be up to, now 9,000 bytes and so forth, allowing a larger frame of data to move across that network. Well, let's take a look at some Ethernet traffic. So I will pull up my capture from the last time, and we'll pull up one of our ICMPs that we looked at before. Even though this is a request reply that failed, that's all right. We'll look at this guy. Let me close all my header fields real quick. My very first, up top here, this is just data about when this was captured. Here is the actual Ethernet header. So if I open this guy up, you'll notice I don't see the starter frame, delimiter, and preamble. No, they're there for timing. So the first field I see is the destination address, the destination MAC address, followed by the source MAC address, and then the type field. What is inside? Well, it's an IP packet inside. That's it. It is super, super abbreviated, if you will. That is your Ethernet frame. There's your Ethernet frame header fields. Now, just a little bit of legacy stuff about Ethernet. We want to at least remember where it came from and how it works, and kind of what we're doing now that works better, if you will. So thinking back in time real quickly, your brainchild behind Ethernet was Bob Metcalfe. Here was his concept drawing for Ethernet. All the devices tapping into the central coax bus. Early Ethernet used those taps that literally bolted around the coax cable, and the devices tapped into that copper cable. This transceiver that bolted around would literally cut through the insulation and make contact with a copper wire inside, and all the devices would be tapped into it. And you would get this structure, this bus structure. Well, eventually they migrated on to using thinner coax and T connectors, so you didn't have to cut into the cable. And I still ended up with this structure here, this coax bus structure. Well, in these days, when you want to send traffic, your computer would send traffic and it would go to everybody on the network. So the way that actually occurred was through CSMA-CD, Carrier Sense Multiple Access with Collision Detect. And what it did, since there was no networking devices out here to control traffic, what it did was your computer would listen for any activity on the network. If it heard any data moving by, and again we're personifying our computers, but if it sensed any voltage pulses going by, as in people were sending data, computers were sending data, it would wait, and it would keep waiting until it sensed no traffic, no voltage pulses, if you will. Once it sent no traffic, it just transmitted. There was no, hey, does anybody want to go next? Nope. Once it sensed no traffic, it just sent, it transmitted. Well, with all of these out here, it is possible to have a collision. The two of us send at the same time because there is nothing to control who goes first and second. So then the rest of this was, once I transmit, we're kind of listening for a collision. If we don't hear any, we're like, hey, I guess it got there, woo! Okay? Hey, it got there, woo! But if it hears a collision, which would be voltage spikes, if you will, two different signals combining and doing voltage spikes, then it would be like, oh, hey, we have a collision. And what happened was all the devices stopped sending, backed off, they took a step back, waited, and then they started the process over again. So if my computer went to send at this and went to send at the same time, they would collide. Everybody on the network would hear it, take a step back, wait. It actually waits a random time, so we all try to start sending at a different time, and then start the whole process over again. That is how early Ethernet worked, the coax bus network worked. When we moved on to a hub, the function is identical. The actual function is identical because all these computers were still doing the same thing because the hub repeats the traffic out to all nodes. So it would, when I go to send, the hub repeats to everybody. So again, the same process is occurring. It wasn't until they started using switches, which, as hopefully you remember from before, switches actually build a table of this MAC address is on this port, this MAC address is on this port, this MAC address on this port. So when it receives data, it actually tries to send it to one and only one port. And because of that, we can have multiple conversations going on at one time. So that whole CSMA CD thing kind of starts going out the window. So modern Ethernet networks are not really using that anymore because of the way the switches are functioning. That's why this is kind of like legacy technology, if you will. But it still is important to remember kind of where we came from and where we are now, or why we are where we are now. So there's Ethernet.